Hi everybody, this is going to be a tutorial for calculating physical properties of solids when we're dealing with rectangular prisms. This is an example of the pre-test that we did in class, and I'm going to walk through some simple things with you, all four types of questions that we're going to have on the quizzes. If you wish to pause this at any time, feel free to. There's also going to be a PDF file attached of the picture in blue that you see on your screen, so we will be taking a look at this object. First thing you do whenever you have any one of these objects that is a rectangular prism is you want to divide it into multiple rectangular prisms. So in this case, I'm going to divide this block into three separate rectangular prisms. So what I can do is we could just, let's say, draw a line here, and we can also draw a line straight down here, and that's going to create for us three separate rectangular prisms. And for the sake of discussion, we will call this rectangular prism A, this will be rectangular prism B, and this will be rectangular prism C. I'm not going to go about putting actual letters on them throughout this, but I think you get A, B, C across. We could also draw lines across here and across here, and you would get separate rectangular prisms also. So in this case, we're going to take a look at A. Whenever we're looking at rectangular prisms, for the sake of just counting them, we're just going to assume that every one of these blocks is 1 by 1 by 1. Although down here it says that each object has a 0.25 inch grid, when we go over that in class, that's a linear distance. And what I mean by linear is, for instance, we have width right here. So the width from one block to one block, when we do our conversions, we're going to say that's going to be 0.25. But to make things easier for us, for now, we're just going to say that everything is just 1 by 1 by 1. That's width, depth, and height. So in this case, we have 2 blocks wide. The total height of this rectangular prism, again, we're really dealing with this area here, is 6. And the total depth back is 5. So in pulling up our calculator, we could just say the calculating volume of rectangular prism is just going to be width times depth times height. So in this case, we're going to say 2 times 6 times 5 comes out to 60. So again, we're going to say that that is going to be A. So we're just going to come down here. What is the volume of the part? We're going to have 60. For rectangular prism B, just moving from left to right, we have 2 wide by 3 tall by 5 deep. So we can just come into our calculator. 2 times 3 times 5 is going to come out to 30. Rectangular prism B has 30 total cubes. You can always just look at one of these objects like it's made out of sugar cubes or it's made out of any kind of a cube. Now this side over here with C, this rectangular prism, it is the exact same thing again as we see over here where A was. So we're going to have 2 times 6 times 5 once again. Come back out. 2 times 6 times 5 once again comes out to 60. We're going to have to add all of those up. So adding up our total number of cubes, we have 60 plus 30 plus 60 comes out to 150. So adding all those up, it's going to be 150 times 0.25 cubed. The reason why we're saying 0.25 cubed is that I've told you that the linear distance for each one of these is 0.25 of an inch. 0.25 is a quarter of an inch. So it's 0.25 wide, 0.25 tall, and 0.25 deep. So we have to take 0.25 and then cube that number. And using our calculator, 0.25 cubed right here, x to the third, is 0.015625. So we can bring that over here, paste that in, and now we have math to do from there. So coming back up, I can take 0.015625 times 150. That comes out to 2.34375. Now that is going to be in cubic inches. That is the volume of the part. That is going to be our actual volume of the part. 2.34375 cubic inches. In the past, some people have been a little tripped up about having to multiply their total number of cubes times this number cubed. A lot of times people will just multiply it by 0.25. We have to cube that number because, again, it's 0.25 wide, 0.25 tall, and 0.25 deep. So this comes out to our total volume of our object right here. There's your answer for volume. Now, moving on to the next question. Number 2, what is the density of gold in pounds per cubic inch? Now, up here I've given you the density of gold in grams per cubic centimeter. So every one of these cubes right here I'm giving to you as in it's a centimeter cubed and not an inch cubed. And we're saying it's 19.3 grams for every one of these little cubes that we see here. So we have to convert. So what we have to do is we have 19.3 here. We have to change grams to kilograms. There's 1,000 grams in a kilogram. So what we have to do is we have to divide 19.3 by 1,000, and that is going to, in turn, give us kilograms. So I'm going to pull up our calculator here, and we're going to say 19.3 divided by 1,000 gives us 0.0193. Now, in order for us to convert from kilograms to pounds, you're going to have to use the sheet that I've given you. And if you look on the screen here at this object, there is 2.205 pounds in 1 kilogram. 2.205 pounds in 1 kilogram. So in order for us to convert from this number we have right here to pounds, because this is how many kilograms we now have to multiply that number by 2.205. And this is going to give us a very large sig fig. Now, we now have ourselves pounds per cubic centimeter. Now we have to go from pounds per cubic centimeter to pounds per cubic inch. And we have to multiply that times 16.38. In wondering where we get that number from, you might remember from previous units, this was back in Unit 3, that in every inch there's 2.54 centimeters in an inch. So what we have to do is we have to cube this number because, again, this is linear. This is just a linear distance. This is just, let's say, a width distance or a height distance or a depth distance. It's not a volume calculation as in cubic. So we have to cube this number. 2.54 cubed is 16.38. So we have to multiply this number by 16.38. And that's going to come out to 0.697. That right there is our pounds per cubic inch. So we have now converted grams per cubic centimeter to pounds per cubic inch. And this will be our number. This is the process that we go through to convert from grams per cubic centimeter. This calculation in number 2 has nothing to do with number 1. There's nothing to do with any kind of a distance here. We're only converting from grams per cubic centimeter to pounds per cubic inch of just 1 cube. That's it, just 1 cube. To find the mass of the object or the weight of the object, all we have to do is multiply our volume that we got in number 1. We have our volume right here, which was 2.34375 cubic inches. And we multiply that times our pounds per cubic inch. Because what we've been able to do is we're trying to find out our volume up here that we've done with this object. And we're trying to say, what's the total weight? Because I gave it to you in grams per cubic centimeters. What's the total weight of the object now? So what we need to do is now multiply that times our conversion number. So as I come back up here, we have this very large sig fig. And I'm going to multiply that times 2.34375. And our total weight of our object is 1.633. We could do 1.634. Let's go ahead and round it. 1.634 pounds. And that right there is your total mass of the object. This is our first 3 problems: how to calculate the volume, how to convert from grams per cubic centimeter to pounds per cubic inch, and now we've gone into the total weight of the object. Again, when we're talking about how to find the weight of the object, it's just volume times your weight density in cubic inches. Our weight density in cubic inches was 0.697. Our volume was 2.34375. Moving on to surface area, this one can be a little bit more involved. I'm going to kind of abbreviate some of it for you, because what we can do is you're going to notice that this object is symmetrical in the sense that I could cut it right down the middle, and it's the same on the left as it is on the right. There's a couple small surfaces that are hidden. We can go ahead and I'm going to walk you through how to find this. So, for instance, on our front of our object, one thing that you can do is you can just change things to different types of squares. So I can even do things, let's say, this way. On the front of our object, we're just going to calculate the total number of squares. Squares are different than cubes. Squares are just 2 dimensions, cubes are 3 dimensions. So here we have ourselves 6 wide by 3 tall, that is 18. Then I can just say 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. There's 30 on the front. The front and the back are going to be the same. So I can come down here and I can say front is 30 and the back is 30. Add both those together, that comes out to 60 for the front and the back. Come back up here again. Let's do our top and our bottom because those will be the easier ones to do. There's 6 wide by 5 deep. Our total width, looking at these 3 surfaces, from the top looking down, I can see this surface. I can see this surface right in here. It goes all the way to the back. And the same thing with this surface. So I can see all those surfaces. I could just go 2 times 5 and add all 3 of those up. That would come to 30. We also have to make sure we include the bottom of the object. So the top and the bottom have the exact same number of squares. So I'm going to say the top is 30 and the bottom is 30. Add both of those up. We come out to 60. Now, I'm going to call these like the left side and the right side. Now the left side, which would be, some people call this the back, it's looking this distance at the object. I'm looking around here, around the corner. We can't see this back side, this left back side. But it's going to be the same surface area as this area right in here. So again, I have 6 times 5 over here. 6 tall by 5 deep. So that's 30 total squares here. And there's going to be 30 total squares on the opposite side. I'm just going to call this left and right. So right has 30, and the left has 30. And once again, that equals 60. I'm going to call the next ones, let's say, hidden 1 and hidden 2, because I can't really see this. I can see most of this surface here, and I cannot see the surface that it would run into. There's this surface right here on the back side of this object, right back in this area here. If we want to look at this actual object here, what I'm actually talking about is this surface right here. We can't see this surface back in here that I've highlighted. So we need to account for that surface, and we need to account for this surface. So going back into our object here, this would be 3 times 5. 3 tall, 1, 2, 3 times 5 deep. That would be 15. The opposite side that we were looking at in Inventor is going to be the exact same surface area because it's 3 by 5. So 15 plus 15 is going to be 30. So coming back down here, I'm just going to call this hidden 1 is 15, and hidden 2 is 15. And that's going to come out to 30 total squares. So in looking at this, we have now counted every possible square we would have to, let's say, paint. So if you're going to paint this thing, if you were going to gift wrap it, we've now counted for every single square of this object. So, moving on, we have to now add all of these numbers up. So, I'm going to say 60 plus 60 plus 60 plus 30 comes out to 210 total squares. 210 total squares. Now, in order for us to find what the total surface area is, we once again have to come back up and look at our 0.25. Now, this is where sometimes some people get tripped up a little bit because 0.25, again, is a linear distance. In our volume equation, we're talking about width times height times depth, but we're dealing with squares. We're only dealing with 2 dimensions. So right here on our front view of our object, this little U shape, every one of these squares, we're only counting for the width and the height of the object. So we have to square that, which means we're putting it to the 2nd power. So 210 total squares. So down here, what we're going to have 210 times 0.25, but only squared when we square the object. So it's going to be 210 times 0.25. So we have 210 times, what's 0.25 squared? So I can come back up here to my calculator, 0.25, and I'm going to square the number right here, and that's 0.625. Coming back up to our calculator, multiplying that times 210, we come out to 13.125 square inches. 13.125 square inches. So there's our answer to that problem. So as we go through here, you can use this to study from. Remember, when we're calculating volume, that is a 3-dimensional space of an object. Volume is the amount of 3-dimensional space an object contains. We have to have that in cubic inches, and we've converted from grams per cubic centimeter to pounds per cubic inch. We multiply those two numbers together, and that gives us our total mass. And then down here at the bottom, find your total number of squares, and this will be your surface area. The biggest issue with total number of squares is to remember all of your hidden views, and then also to remember to count the bottom of the object. A lot of times people don't want to count this bottom side. You have to make sure that you're counting both of your surfaces. Good? I hope this prepares you well for any exams that you might take over calculating properties of solids out of Unit 5 in Introduction to Engineering Design. Have a good day.